Right, so our next talk is also on attribute grammars, and it's called Nanopass attribute grammars, and Nathan Ringo, also from the University of Minnesota, is going to talk about it. Floor is yours.
Yeah, hi. I'll be talking to you about Nanopass attribute grammars. This is joint work with Lucas and Eric. And yeah, there are these two approaches that exist in the literature, Nanopass compilers and attribute grammars. In Nanopass compilers, you're trying to design a compiler as the composition of a lot of tiny, simple passes. In attribute grammars, on the other hand, you've got your one big syntax tree, and you've got a bunch of attributes decorating it, and you use these to perform analyses. Nanopass compilers have a couple wins to them. You can sort of rely on your one big correctness property of semantics were preserved. On each of your passes, if each of your passes is semantics preserving, the composition of them should be as well. So you can test them by saying, hey, was this actually semantics preserving for some particular input? And you can reason about their correctness in those terms. And since these passes are tiny, isolated little things, this is actually pretty easy reasoning to do informally. On attribute grammars, on the other hand, you sort of have like this a frontier of correctness, where you have to try and figure out what does it mean for this attribute to be correct in the context of this whole AST. So it's still obviously very possible to reason about the correctness without too much difficulty, but it can be a bit trickier than just having this one property that you're always thinking about. On the other hand, attribute grammars are a lot better when you want to check properties of the compiler itself statically. We have analyses for checking that it's well-defined, non-circular, all these things, and they work great. They're also great for talking about complicated data flow, analyses that do need to walk the whole tree, collect up information, do fun things with sets. Great fun, easy to write in attribute grammars, not so much with existing Nanopass compilers. So the goal of this work is to get the best of both worlds. Check all of these green. So first I'll go over a bit more background about Nanopass compilers. In the Nanopass approach, as I said, you're splitting the compiler into these tiny passes, nanopasses in reference to their size, between slightly different languages, in that you might define a variant of a language. A lot of these passes, 80% of them roughly, are going to be things that are just lowering or simplifying or normalizing the program. Say you're working with an imperative language that has both if-then and if-then-else. You might want to normalize away the if-thens because you can just put an if-then-else with nothing as the else case. You also might want to normalize things like if you have polymorphic add production. You might want to change that to be integer addition once you know that the types are integers. This will make other passes later on easier to write because you can just dispatch on the production, like in an attribute grammar way, without having to think about, hey, I need to check the types. And generally, yeah, this will just make later passes easier. For the other passes that you'll have, they'll generally be doing kind of classical compiler things like optimizations, type checking, these sorts of things. Here, your passes aren't necessarily going to be super small anymore, but the input should be pretty tightly constrained, thanks to all the lowering you've been doing. And you can still reason about them with your one big property of, is the semantics preserving? Yeah, that's that. And this was originally introduced as a schema library at ICFP 2004. And this is used in the Shea scheme compiler. And as far as I know, they're very happy with it. So just to make this more concrete, I'll sketch out an example compiler, or an example of some passes for a compiler for an imperative programming language. The first thing we might do, say, is get rid of if-then, as mentioned before. So we'll define a new language, we've got L0, which is our initial source language, and we might define a new language L1, which is exactly the same thing, but without the if-then production. We'll then have a pass that goes from L0 to L1, transforming according to that rewrite rule. We might then define the next language, L2, where the difference between L1 and L2 is that types are fully explicit in L2. Every expression has a type attached to it. And we could, again, have a pass there that does that. We could then have a language L3 in which all the polymorphic operators have been transformed into monomorphic ones. So where before you had a polymorphic addition production. Afterwards, you'll have int add, float add, complex add, whatever other addition productions you might have. Maybe then you're going to get rid of complex numbers because your language has records and your backend can deal with those. You don't want to have to deal with complex numbers. So you could lower those in another pass. And L4 would again be like L3 with some stuff removed. You keep on having a bunch of passes like this, of this nature. And eventually you'll get to the end where the last thing to do is you can like flatten your expressions. You can take expressions that have other expressions as their children and say, I'm going to make a new atomic expression that has integers, variable names, may float literals, nothing else, and translate down to there. And then at the end of your chain of languages, you'll have a language that's trivial to translate to assembly. Now I'll have some background on attribute grammars. You'll see if you saw the previous talk, we can't just share trees, we can share slides too. So yeah, attribute grammars, you represent the structure of the object language program as a tree. You then have attributes you're putting on it. Synthesized attributes are going bottom up. Inherited attributes are going top down. And yeah, formally, it's context-free grammar. You put on synthesized and inherited attributes. You have a relation for where they occur. And you have some equations. Attribute grammars as we know and love them. So we can define some criteria that a Nanopass attribute grammar formalism should have in order to merge these two different bodies of work. First off, we need to easily be able to identify the syntax of many different languages. It shouldn't take much more effort than saying L1 is L0 without the if-then production. We certainly shouldn't have to re-specify the entire language. The Nanopass formalism, like this is a large part of the point. This is super easy to do there, well supported. Emulating this in attribute grammars is annoying. You're gonna have to list out all of your non-terminals again and then copy all your productions over. If you need equations, write those again. So enough boilerplate that you just don't do this. The second criterion would then be checking that whenever you're building a tree, you're actually building it in the language you expect it to be in. So if you're in the output of some transformation, and it should be, for example, removing if-thens, you better not be adding any new if-thens. And this applies later on too. If you're way after that and the language just if-thens are completely unrelated, you better not be producing any. This also applies to analyses that you want to do on the tree. If you're computing types and complex numbers aren't supposed to be there, or getting the results of type checking and complex numbers aren't supposed to be there, you better not be there. The Nanopass framework kind of does this. It checks types at the boundaries. Like at the boundaries of a pass, it will check to say this tree doesn't contain this thing I'm expecting it not to. But within a pass, there's nothing checking that your intermediate results are going to be in the language you expect. And in attribute grammars, since we don't really have a way of talking about these sublanguages conveniently, nothing really there. Our third criterion would then be that we can specify these transformations pretty easily. For the large chunk of them that are like pretty much trivial rewrite rules, we should be able to just write them down with about that level of complexity. This shouldn't take half a page, it should take 3 lines. For either one of the if-then or making addition not be polymorphic. We especially shouldn't have to write things saying like, oh, how am I going to handle while loops? Well, the transformation should just be applied recursively. It should just work. The Nanopass framework and the Nanopass approach make this pretty easy. Implicitly, you get the clauses that you left out saying, propagate this thing recursively. And in attribute grammars, there are a lot of extensions that add this approach. They're not built into the formalism, but yeah, they more or less work. So we need to make sure that we preserve this. Our fourth criterion is that when you're describing your semantic analyses and implementing them on a language, you should only have to write them for the things that are in that language. For example, once we've removed if-then from the language and we're doing type checking, we shouldn't have to care about if-then or think about it ever again. We also want this to be checked statically. We'd still like to keep the nice things from attribute grammars where we know you're not missing any equations, and know that at compile time without realizing, hey, I forgot a case, and getting a compiler crash. The Nanopass framework doesn't really have a nice mechanism for doing semantic analyses. Like you can always just bail out and call scheme code, but the scheme code there isn't going to check and like statically tell you, hey, you forgot a case. And attribute grammars, like missing languages again, kind of hurts you here. If you're trying to avoid defining n copies of your entire grammar for your n different languages, you're going to have a bunch of missing equations. Like if you're trying to share the same if-then, like if-then is going to still have an attribute occurrence for something like typing that came from statements. So it's going to yell at you, oh, you need an equation here. You can make that equation just crash to tell the analysis to go away, but But then you've kind of lost the point of the analysis. What if you did actually need it? So yeah, they don't really get to check that box either. Lastly, we want to keep the results of analyses across sequential tasks. This should actually be a check for Nanopass. But if we have like a type attribute we computed during type checking, we want to be able to like save this and move this across passes pretty easily, even as we're like rewriting the whole tree to get new trees. In the Nanopass framework, it's reasonably syntactically convenient to just add this as a new child and say, after this point, I've got a new child, and that's my type. It's a bit of boilerplate, but it's very manageable. Versus in attribute grammars, there isn't a great way to do this. Like if you're in the normal approach where you've just got one tree and you're doing a bunch of computations over the tree, the attribute's demanded when it's needed, and you don't really need to think about persisting it. But once you start building new trees, nothing's copying that attribute over, so you don't get to keep it by default. So we have a formalism that we think satisfies these criteria, our Nanopass attribute grammars. We've got three main parts to them. We've got our collection of language elements, which we call E. We've got a family of languages, L, and a composition of passes, C. So the family of language elements is basically a huge, not necessarily well-defined attribute grammar, with every non-terminal that we ever use in all of our languages, every production that we use in all of our languages, all the equations, everything, all in just one big kind of soup. So it's not going to be well-defined because you're going to be missing equations like how do I type check an if-then. However, you can type check this actual specification. I'm going to go over the rules in a bit of detail because there's going to be another type checking looking analysis later. So here we're looking at what it looks like to type check a production call, like a call to a production P with two children, T1 and T2. We've got two judgments here. The first one says, given the context of our whole specification and the production we're in an equation for, does some expression E have type tau? The second one says, given that same context, so we're in some production's body and we've got the whole rest of the specification as context, is this equation well typed, x dot a equals E? So an example rule for this would, to check to see if a synthesized equation is well typed, goes something like this. You're trying to check the equation at the bottom, so you look up what's the type of the production, you get the signature here, you say, hey, X, the name of the left-hand side, matches, okay, cool, and A is a synthesized attribute, it's in our set of synthesized attributes. Cool, this applies. You then check that the A attribute actually occurs on the non-terminal, X, and then that the expression has the right type, whatever type we're looking up from E, the context mapping attribute names to their types. And yeah, assuming that all works, it should be type correct. Importantly, anything we're doing on E, we only do once across the whole compiler because it's not split into sublanguages. So when we're doing type checking, we're only doing it once. There's also another thing we have in E, which is not traditional necessarily in attribute grammar systems. We have a notion of annotations. These are, I believe, also known as, sorry, not implicit attributes, inherent attributes, I think, in other systems. But when you construct the tree, you can provide values to it for that occupy the same namespace as attributes. Sort of in a sense, an synthesized attribute gives the attribute value from the node itself. An inherited attribute gives it a value from its parent. An annotation lets you give it a value from whoever built the tree, who's not necessarily its parent, especially when you're talking about these transformations. So here we have like an add of the integer 40 and the integer 20, and we're explicitly passing int tie as the type for the annotation. So if an equation depends on e.type, where E is this tree, it'll get int tie, as long as there's like, because no equations will be there, they'll be asked for what its type would be. These will come in handy later. These are, yeah, these are just in E. So in our collection of language elements L, we've got languages like the L0, L1, et cetera from before. They're pretty much just subsets of E. You've got some productions, non-terminals, attributes, equations from E, and some of the attributes are marked to be annotations. So within an individual language, an attribute is either a normal attribute or it's an annotation. So it'll always just be pre-computed and sitting there. Within each language, you should have a well-defined attribute grammar. So you can still use existing well-definedness checks from the literature there. And yeah, you'll have to run it once for each language, but this is pretty much acceptable. They're fast. So we need a way to specify these things. The first way that you'll probably do at the very start of your compiler is to actually list out everything that's in it. So in the syntax of our prototype system, this is how you'd list like the start of the of an imperative language. You'll say, hey, I've got statements, that's a non-terminal. They've got some productions. You list them out. Any non-terminals that you list, or any productions you list that are non-terminal will get included, and any attributes that are present and not annotations will become part of the language as well. So this, of course, would go on pretty long. Like this would be your whole language, whole source language that you intend to process. Then there's the second way that actually provides like the convenience of being able to extend languages. You can say, I'm defining a language L1 that extends L0 by removing the if-then production. I might then say new attributes are present that weren't present in L0. Like now I can compute typing. I might have an environment. I'll have other attributes. Everything I need to do type checking. I could then have another language, L2. These are the same ones from the example before, where after L2, we're doing type checking as we move from L1 to L2. So in L2, we annotate expressions with types. So the type should already be computed by the time we're in L2, and it'll just be sitting there ready for use. So here when we extend, all we do is we add a type to the set of annotations on expressions. We could then have another language, L3 extending L2, where we get rid of addition as a production, but instead we've added in our complex integer and floating point addition productions, which yeah, may make other tasks easier. So once we have our languages and the rest of our attribute grammar parts ready, we can then define transform attributes. Transform attributes are how we map one language to another. So you'll write some, like for the removing if-then, you'll have an equation on the if-then production saying that the result of removing if-then is that if-then else there. You can like just demand the attribute on your children to get it recursively applied, and then you'll build a new tree and return the tree. The benefit of using transform attributes over a normal higher order attribute is that they're going to generate equations for you. On all of the other statements and all the other productions across all the non-terminals in L0, you're going to get an equation automatically generated that propagates the transformation recursively downwards. So this is all you need to write for the pass that's going L0 to L1. And the rest is generated for you. Similarly, to go from L1 to L2, you only have to write that one line. The type attribute is computable on L1, so when it's present as an annotation in L2, we just compute it and put it in the trees. And all those equations are automatically generated, so you've got one line of code for that whole pass. You can have more complicated equations too. When we're going from L2 to L3, removing the polymorphic add and having specialized ones, we can have a whole expression here that's looking at the type annotation, doing branching on it, doing all these things, producing new trees. And we can analyze it and know we're always producing a tree that is in L3. And anything we're doing on type is valid for type being in L2. And type will get moved to L3 as well, because types will get a generated equation saying, here's how you map a type from L2 to L3. Because type doesn't actually change, that's actually a no-op, but if it did, you'd be able to apply it there in the annotation as well. So, like, to do this whole check, we have this idea of language correctness. In the same sense that we have like a type correct program, we have a language correct program. In the same sense we have a type checker, we have a language checker. This ensures that any trees that we build or accept are in the language we expect them to be in. When we have a transform attribute, it's always operating on, like you have a fixed source and target language for it. So it should be producing trees that are in the target language from ones that are in the source language. Higher order attributes are going to be in the source language generally. You're using them for optimization. If you're using them to, do analyses for the purposes of making optimizations, generally you're going to be doing these analyses within the source language. So this makes sense as a default. There is some subtlety here to make sure that when you're doing an analysis, anything that you're computing isn't going to have something weird showing up you expect it to be gone. For example, complex numbers. If you're doing some analysis that was written before complex numbers were removed, it might not pass the language check afterwards. Probably you want to save it as an annotation, and then it'll get mapped properly, but possibly it might just be wrong. Either way, the language correctness check will flag it. So here we can look at the top level rules for it, a couple of the top level rules. We have a pair of judgments again. The first one saying that in the source language L, and given our same context, some expression is language okay. In the same way something would be like type okay, it would pass the type checker. It's language okay, it passes the language checker. Then we also have a judgment saying that some expression E is in a target language, given context and source language. So the difference between the source and target language being different is, important for keeping track of them. In the case of inherited and synthesized equations, where the attribute is inside our set of inherited or synthesized attributes for the language, we are just propagating the check downwards to the expressions with the same source and target language, L for both, when we're checking against the equation within a certain source language. Contrastingly, inside the transform equation, when it's inside the set of transform attributes, we're actually going to look up what is the source language, what is the target language of that transform attribute, and when we propagate it down, we're going to check they match. We're also checking to make sure that the source language of the transform attribute actually matches the one that the attribute is put inside, but the prototype system always ensures that's the case. We'll then have language checking rules like this. This one's checking that when you call a production constructor, it's actually building the production that's in the right language. So when you call the production constructor P prime, it checks that P prime is in the set of productions for your target language. Then it looks up the signature, says, okay, it's going to produce an X. And then it should, there's something that the X was used for, that this is a simplified rule from the full rule that's in the paper. Ignore the X. Then we check for each of the children that they're valid in the target language, L sub T as well. So if all the children are valid in the target language and the production is actually in the target language as well, we should have a tree that's in the target language. None of these rules are that complicated. They mostly do just look like we're propagating down, check that this is in the target language until you hit a call to an attribute, and then we check what a language should this attribute be producing. They're pretty straightforward. The analysis is almost a top-down pass. It's pretty easy, pretty fast. For the final part of the Nanopass attribute grammar formalism, we've got compositions. Here you pretty much string a bunch of transform attributes together and say the compiler is the composition of these in a normal function composition-y way. The source and target languages have to match up, of course. But yeah, it's simple, easy, it's composition, and we get nice compositional properties. So we at least need one to just talk about what are the semantics of this program, but it actually can be useful to have several of these. For example, you might, testing is one of these big advantages. You might only want to run a couple passes of the compiler for testing purposes. If you've got some optimization passes, you might also feel like twiddling them to see different things. Or if you're trying to write a compiler like GCC that has multiple different source languages, you could do that too. You could share, for example, languages 10 and on between multiple different front ends that all eventually translate to that shared language. So in future work, we'd like to allow attributes to explicitly identify their language. Right now, you just get those two simple rules of transform attributes always have a fixed source and target, and synthesized and inherited higher order attributes are always in the source language. There are cases where you might actually want to say, this isn't always in the source language, it's always in L3 in particular, or L7 in particular. In some sense, attributes are implicitly polymorphic, and we'd like to give the user the power to say, we don't want that polymorphism. We'd also like to implement this in a proper, full-featured attribute grammar system. We have a very rough prototype right now, to prove that there's no sudden and hidden gotchas with the analysis, pretty much, and a sketch of a Go compiler in that. But it'd be nice to have this in a proper thing so we can try out writing a C++ compiler. Maybe this would be in Silver, and maybe this would just be a new prototype system. Yeah. So in this work, we've extended attribute grammars to allow concisely specifying a bunch of different languages, transformations between them, and then allowing for the analysis of completeness, type correctness, and this new language correctness property. We'd like to thank the anonymous reviewers for their helpful comments on improving the paper, and I'd like to thank all of you for your attention. Do you have any questions?
Right, let's thank the speaker. Questions? Yeah, could you please walk to?
So thanks for the talk. I think it's a very interesting framework that you can use to develop a compiler and also address the expression problem to some extent, because we know that we have different data types and different attributes in different phases, so they can express this in this language. So I'm wondering, do you allow that the user can like inject arbitrary code in the attribute grammar so that we can do really, really complicated things in real world compilers? Like even you want to resolve the name of a method, you may even, let's say, open some library binary file, and you have to decode like the signature of that method so that you can do type checking. And this, I don't think you can easily, have some domain-specific language to do that, but rather a general-purpose programming language.
I mean, anything extending like what sorts of analyses you can do in an attribute grammar should apply pretty cleanly here. Like if you have some way if you need to jump outside of the formalism to do some low-level parsing packed binary data or whatever, that should just work if you put that in an equation, because synthesized and inherited attributes are computed exactly as before, and transform attributes are computed like higher order attributes are. Does that address your question?
I think my question is, if you can inject arbitrary code, I think this problem should be solvable.
Like into the compiler?
Yeah, in the grammar maybe. In a language definition, let's say, you can inject some code, some actions.
In an earlier version of this idea, we had a notion of like open and closed languages, which kind of mirrors Silver has a notion of open and closed non-terminals, where you say that, oh, well, maybe there's some unknown to me currently productions that might end up inside this language later. It ends up being tricky and subtle. I think right now our position is essentially that forwarding, if you want to have an extensible front end, forwarding is the right way to go there. And you might forward your way between L0 and L1. And then once you're in L1, then it may make sense to do all your Nanopass stuff to do the middle end and back end of the compiler.
Okay, yeah, I think we can talk more during the break.
Okay.
Thank you.
Any other? Yeah.
Well, thank you for your great talk. I suffer a lot with using high-order attribute grammars, and I miss some of features you present today. But for instance, I wrote several grammars where I did a lot. There was a lot of computations, attribute computations, that before we could rewrite the source into the target language. The slides you show you were more kind of a syntactic evolution of the language. Can you do that mapping dependent on attributes?
Yeah, that's where annotations come in. So if we look at like this one, for instance, in L2, we're expecting to have the types as annotations. So the computation's already been done and we stored it there. We're just storing it so that it's easy, so we don't have to recompute it after rewriting. But you can then dispatch based on the type. You can use it as an annotation. If there were more attributes present on L2, you could use them too.
Okay. Thanks.
Yep, go ahead, Thomas.
So in one of your opening slides, you mentioned that attribute grammars are popular because of it's easy to reason about the data flow. So could you reflect on to which extent that is still possible for your framework? Like how easy is it to understand how information propagates from one language to another? And for example, can you make like nice diagrams or visualizations of this?
I don't have anything currently that makes nice, pretty pictures, but I mean, conceptually, it's not difficult. A nice property is that between like your languages, like when you finished going from L1 to L2, the tree there should be like a genuine tree without any like secret dependencies backwards. If you want to like print that out or make a GraphViz chart of it, should be no problems with doing so.
Right, let's thank the speaker once again, and everyone wants to.